Yo-ho, me mateys, and welcome to Neuroscience Fundamentals for Pirates, with me, Captain Alt. Now, just briefly, what are our learning objectives for today? 1. We're going to be able to identify the main components of your plank, i.e. your neurons. 2. We're gonna identify your brain and central nervous system in the context of your vessel and crew. And 3. You're gonna be able to answer me old quiz at the end. Yo-ho! Here we have a real neuron lying in your brain. Millions, trillions of neurons firing at different parts and places all the time. Loads, me mateys. Now here you have your dendrites. Dendrites are your little sensors. It comes in contact with these puppies over here, your axon terminal buttons. Alright, excuse me parrot, by the way, that's just old Sally. All of this good stuff is all your axon terminal. This here is your synaptic cleft, me mateys, making a whole synapse, a connection, if you will. This is how we communicate chemically, electrochemically. On the end of your dendrites are little bumps to provide more surface area. These are your spines, your dendritic spines, mateys. This huge portion here, this mighty area, is your cell body or your soma. And this is the nucleus. Just like all the other cells in your body, these neurons, they got nuclei too. These little yellow rings are made up of oligodendrocytes in the CNS and Schwann cells in your PNS. We'll be going over the CNS and your PNS later, potentially. These are the lipid-rich, fatty substances that wrap around your axon. Your axon is this big portion, the long line. This is why we call it your plank. This is your axon. Now these sheaths are called, they're made up of a substance called myelin, which is basically just fat. This helps signal to go through down the axon to the axon terminal much faster. And supposing this neuron's getting a signal from many other neurons. Say these are the axon terminals. This part, we talked about that just a moment before. Jesus Christ, old Sally, get it together. They're connected at synapses from millions of other axon terminals. From these little spiny little apparatuses. See, they send a little signal. We won't be getting into how that works today, mateys. Say in blue, we show the signal. It comes through, down the axon terminal of the presynaptic neuron. Presynaptic to this neuron, which is presynaptic to any other neurons. Say, there's another one over here. Here is another dendrite. Are you starting to see how it's all a loop, mateys? It's all a loop. Say it's coming through the dendrites, and it reaches a little bump a hillock, if you will. Right here, mateys. This is your axon hillock. Your axon hillock undergoes a process called summation, which is essentially counting up all the incoming signals from all the other axon terminals. It's counting up the signal. And it's waiting. It's sitting there waiting. Jesus Christ, Sally, get it together. It's sitting there waiting. It's waiting for what? Well, while it's waiting at a difference in voltage between inside of the cell, intracellular voltage, and extracellular voltage. There's a difference of negative 70 millivolts, mateys. Right here at the hillock, what it's doing, it's waiting to see if it reaches negative 55, mateys. And if it does, oh, it's beautiful. What happens is it passes through. It goes down. It's getting sped up with all this myelin from oligodendrocytes and Schwann cells. And probably more, but we didn't learn that in our courses. And then what does it do when it reaches the dendrite of another neuron? It goes down. But who's to say that neuron will fire? Who's to say it'll reach this golden point of negative 55 millivolts, mateys? Now I want to show you my masterpiece. Now that we know the basic components that comprise ye plank, here it is, your trusty old plank with your neurons. And more specifically, the plank is like their axons. Now, this is a sagittal view of your vessel and crew, meaning it's like side on, mateys. Working from the bottom down. Sorry, too much rum. First is your old sail. That's kind of like your cerebellum. It refines and smooths muscle movements, allowing your vessel to be transported from point A to B once it receives a signal from yourself, the captain. The captain is your frontal lobe, including the motor cortex and your basal ganglia. The basal ganglia is a little bit more like... it's a little bit hard to explain using a pirate analogy. But this is you, the captain. You're the main decision maker. You're analytical. You're rational. You think you know what's going on, but you don't have a goddamn shodden clue. This is old Sally the parrot is like your temporal lobe. Your temporal lobe deals with language. It can identify the meaning of words just like a real parrot. That's why I was very proud of this analogy. And it deals with semantic knowledge of language, and that. It also is the one that listens. The temporal lobe, it listens. Temporal meaning kind of like your temples, because it's like, wait, the temporal lobe is totally not. Oh, it is sort of on the sides. It's like, but it's like below.
Yeah, it is.
Okay. Let's move on to your thalamus. Your spyglass operator is like your thalamus, always looking on what's over yonder, seeing what's out there. It's like your sensory central place, the thing that sees, the thing that hears most incoming, if not all, sensory inputs are relayed through the thalamus. What happens when your thalamus detects something it doesn't like? That's where your advisor comes in. A little bloke next to the spyglass operator. He tells it to the rest of the crew if something really shite is in front of you. If you're headed straight for a storm, your amygdala detects this. It freaks the fuck out. And it activates your sympathetic nervous system, which is like your cannons. It fires when you've detected something hella bad going on. Signals it to the rest of the crew, and your captain tells everybody to prepare, to ready your cannons and get ready to fire. In addition to this, because your amygdala is close to your thalamus, it has first say whether to alert everybody, to freak everyone the fuck out. However, it's much further away from the captain. Everyone else already starts a sympathetic nervous system response before it can be interrupted by your frontal lobe. Yourself, the captain. The captain can tell everyone, fear not, that Storm, she's a bitch, and we can go right through her. And everyone will go, oh, okay, it's chill. Your treasury in your captain's quarters is like your basal ganglia. It holds the nucleus accumbens, your doubloons, which is kind of like your reward. Every time your nucleus accumbens is stimulated with dopamine, lads. Dopamine, doubloons, money. You store it, and your basal ganglia is feeling good. I don't really know how to explain this with pirates, and I also don't really know how this stuff really works yet. So I think we're just gonna move on, mateys. Basically, when you do something good, maybe you rob another vessel, and you steal all their money, it feels nice to fill your basal ganglia with doubloons, triggering your nucleus accumbens. So it's kind of, I've labelled your treasury as your basal ganglia and your doubloons like your nucleus accumbens, but that's not really, it's kind of hard to understand it like that, mateys. Your basal ganglia holds the nucleus accumbens, but your doubloons are more like the dopamine that trigger the nucleus accumbens to go, that's nice. Your bookshelf in your captain's quarters is like your hippocampus, but only for a short while. Not many people understand that. They think it's like where you stole all your memories. And I don't quite understand it, but the hippocampus is more like, it's more like a to-do list, you know. It's temporary. It stores short-term memories. And when it's time to either discard it or to keep it in long-term memory, it may go elsewhere, lads. Trusty plank, we talked about those. These are your neurons. And another note, why is it like your trusty plank? Well, it'll either fire or it won't fire. Either you send someone to their doom down the trusty plank, your neuronal axons, and it fires all the way, or it doesn't. It does nothing. You keep him there. You don't fire. It's called the all or nothing principle, mateys, and you can Google it. Of course, have your emergency rope. These are like your transporters, going back to the neuron. This is your synapse. This is where it connects to another neuron. And inside, it looks like this. Your vesicles are like these little lumps of neurotransmitters, mateys. We'll draw them in pink. These are your neurotransmitters, mateys. And calcium comes in through a little ion-gated calcium channel. And your calcium comes through when it reaches 55 millivolts. Your calcium comes through and pushes the vesicles to the membrane of the axon terminal. And it undergoes a little process called exocytosis, mateys, which is where it kind of merges with the membrane, forming a new opening a bit like this. And the neurotransmitters are sitting here, and they get forced outwards. Now there's neurotransmitters everywhere. Holy shit, lads, we don't need that many fucking neurotransmitters. This is this part, the dendrites. these have what's called ligand-gated ion channels. These are like gates that are locked. They need keys to open them, mateys. Keys which may be opened with these neurotransmitters. These neurotransmitters are pumped out all over the fucking place, just in case it actually hits the right spot. Right over here. They unlock the doors. Notice these are called ligand-gated ion channels. Neurotransmitters cannot pass through. It's a common misconception, mateys. Neurotransmitters don't go through into the postsynaptic cell. Only the ions. The ions pass through. I don't know why they're also blue. They're blue. They pass through into the other cell. And these ions are positively or negatively charged, and they either cause an inhibitory or excitatory effect on the postsynaptic cell, which basically makes the voltage, let's say it's -70 at resting potential, the difference between intracellular and extracellular charge, mateys. It basically, if it's excitatory, it makes it go up. It makes it go closer to -55. Or if it's inhibitory, it makes it go down, mateys. It makes it go down. Now, here's where we get to the transporters. The potassium and sodium transporters. These are like your emergency rope in case you send someone down and they don't need to be there. You say, oh shite, I changed me mind. Pull her back in. And they're a little pissed off and they come back in. They climb up your rope because you've basically got an additional pump. Here, you've got a pump. This is like your lifeboat, which sucks up all the excess neurotransmitters. Because there's too fucking many, you don't want it floating around in cerebrospinal fluid, mateys. Now, you've also got these glial cells. The glial cells form these myelin sheaths. Right? These are like their feet, but they're a whole nother cell. Just like this, mateys. Say, this is a glial cell, an oligodendrocyte, if you will. This would be an oligodendrocyte. This one can also come in and vacuum up all of the excess neurotransmitters. And they travel up the glial cell. And it sucks it up and gets rid of it. So these two processes, the sucking up from the glia, the glial cells, and sucking up from these transporters, these I suppose they're like potassium and sodium transporters. These are like your lifeboats. In case you send someone to walk the plank, you send them overboard and you change your mind. They can suck them up, they can climb back up. That's called reuptake, mateys. You have to have something wrong with you to watch me channel. You've probably heard of SSRI, selective serotonin reuptake inhibitors. If you think of it like inhibiting the reuptake, it cuts this off. It makes an SSRI comes in and says, fuck you. If they send them overboard, they send them overboard. Which means that these people, we made it pink, we'll make it pink. These little people overboard are floating around in cerebrospinal fluid, lads, and they can float away. Your nervous system is comprised of what I like to call the 7 C's. You probably know what the 7 C's are if you're a real pirate. You think it's all the different C's that you can transport your vessel over. But it's nonsense, mateys. Well, it's true, but also the 7 C's, from a neuroscience perspective, mateys, is all of the different C's that I've capitalized on this handy little chart. Your central nervous system is your brain and your spinal cord. The little line that is your spine. See, it rhymes. So that's 2 C's, central and cord. Peripheral nervous system is what extends out from your spinal cord and back into your spinal cord, like in your arms and your legs and shit. This is your somatic nervous system, which controls your skeletal muscles, and also your autonomic nervous system, which is comprised of your sympathetic nervous system and your parasympathetic nervous system. We talked about the sympathetic nervous system. These are your cannons, and your parasympathetic calms them down. It's like your rum that counteracts and gets everyone ready to reload their cannons and chill out with sea shanties. Finally, me quiz. My question is, if your thalamus, your spyglass operator, were to detect a potentially threatening stimulus, who'd be in charge of relaying it to the captain and the rest of your dog crew and sounding the alarm for your cannons, your sympathetic nervous system, to fire? Post your swashbuckling answers in the old comment section below, mateys. First Lily Liver to answer correctly will be rewarded with 5 gold doubloons. That's it from me and Sally today. Make sure to stay in school. Stay swashbuckling, mateys. Peace out.